Part B of Lesson 1.3 is about rocks. Part A was on minerals, and we know that minerals are the building blocks of rocks. And here we have a little more formal definition. Rocks are an aggregate of one or more minerals, a combination of one or more minerals. Here we'll cover the three types of rocks, the main types: igneous, sedimentary, metamorphic. And let's start with igneous rocks, and those are formed from magma. Remember, there's lava, which is magma that's come out of the ground. When that magma has come out of the ground, we say it's extruded, and so we have two different types of igneous rocks. Extrusive, those are igneous rocks formed outside Earth's surface. They cool quickly. They're usually more fine grained, like rhyolite. That's what this is in this example here. Because they cool faster, there's not as much time for individual mineral crystals to get bigger, to grow. But an intrusive igneous rock, that's formed inside the Earth's surface. They cool slower. They're usually more coarse grained. You see these coarse chunks in there. So that's granite. And granite and rhyolite have very similar elemental compositions. If you looked at the percentage of silica, percentage of iron, things like that, they'd be very similar. It's just that rhyolite has cooled quicker. The crystals are typically smaller. Now you can see some larger crystals here in that rhyolite, but for the most part, I mean, we can't really see anything that looks like a crystal, but the granite, it's just a lot easier to distinguish crystals. Now, just an interesting fact, extrusive, more dense basalt, that makes up most of the ocean floor. And basalt, it has a higher iron content and a lower silica content than granite does. Granite is intrusive, formed inside the Earth's interior, beneath the surface. It makes up most of the continental land masses. There's usually some sedimentary rock above it, but at the bottom of that, the basement rock, sometimes it's called, it's granite, not basalt. And so that is interesting that basalt, which is more dense, would be down at the bottom. It would sink. Granite would be less dense, float on top. And so that does kind of make sense that the ocean floors are mostly basalt, while the continental land masses are mostly granite. Now we can think about that rock cycle from Part A of Lesson 1.3. Think about that again. Plutonism, that's basically the formation of igneous rocks beneath the Earth's surface. So a body of magma that cools under the Earth's surface. It never makes it up to the top. That's called a pluton. And so that forms intrusive rocks like granite and some other ones, granodiorite, diorite, gabbro. Then volcanism, when the magma comes up and out as lava, we get extrusive rocks like rhyolite, dacite, andesite, basalt. Now, it wouldn't hurt to try to draw this diagram. The different types of rocks, they can get confusing, mainly because there's several things going on that help us identify the different types of igneous rocks. We have darker ones, which are more mafic, it's called. So the darker it is, and really it's the more iron it has in it, magnesium also, that causes it to be more mafic. Lighter, they have less iron and magnesium, so they're called felsic, more felsic. And we also see some temperatures here. More mafic minerals, they cool at higher temperatures. So they would be the first to cool and to form solids. And so all of this left-hand part of this column, or this chart, that's minerals, different types of minerals. And then remember, those are the building blocks of rock. So if we have peridotite, we see that it's made up of mostly olivine, but then also pyroxene and anorthite. Now the extrusive form, if that magma that had those abundances of those minerals, if that came out as lava, that would be an extrusive rock. That would be basalt. And we see there that basalt, it kind of has the consistency of something between peridotite and gabbro. And now we see down here this extrusive rock, rhyolite, it's going to be lighter in color. And if we went to a volcano and we saw a really dark rock on the outside of the volcano and a really light colored one, we could be confident that the darker one was for sure, it was more mafic, possibly basalt, and the lighter one would be more felsic, possibly rhyolite. And we can see that rhyolite, it doesn't have any olivine in it, any pyroxene, any anorthite. It's mostly potassium feldspar, and then quartz and some other minerals. So looking at this chart and then thinking ahead to your homework, this chart, there's many questions you could ask. Here's a couple of examples down here. Look at the first one. Which extrusive rock would have more iron, andesite or dacite? Well, this direction here is increasing silica, and so the other direction is increasing iron. And so we want to compare andesite and dacite. Well, andesite, that would be the one with more iron. Why don't you see if you can answer that second question there? Pause the lesson. So that second question, which mineral has a lower melting temperature, quartz or olivine? Well, here's olivine. It has a pretty high melting temperature compared to quartz. So quartz would have the lower melting temperature. And so that's what we would write for that one. So be very familiar with this chart. You could even put a piece of paper over the chart and then trace the diagram. Drawing it is one of the best ways to get familiar with it. Well, let's move on to sedimentary rocks. And sedimentary rocks, those are formed from eroded products of pre-existing rocks or mineral precipitates. So they can be formed from pre-existing rocks, or they can be formed from mineral precipitates. And sediment, that's usually classified by size, and we can see this diagram over here. 256 millimeters, that would be about 25.6 centimeters, which is about 10 inches. 10 inches and up, we consider that a boulder. And then between about 2.5 and 10 inches or so, that's a cobble. And then we get smaller and smaller: pebbles, sand, silt, clay. 0.002 millimeters and smaller is clay. And let's apply some of our unit multipliers here. Think about an example here. What is the maximum diameter of a clay particle in inches? Well, the biggest it can be is 0.002 millimeters. So what would that be in inches? Well, let's just think about that. Write down what's given first, 0.002 millimeters. We want to convert that to inches. And so what we need to do is think about inches, that's English system. Millimeters, that's metric. We convert from English to metric using that 2.54 centimeters equals 1 inch relationship. So let's convert millimeters to centimeters first. And hopefully you remember that in 1 centimeter, there's 10 millimeters. So we have 1 centimeter over 10 millimeters. And therefore our millimeters cancel out. It's always good to just keep up with things, make sure things are canceling the way they're supposed to. And we're trying to get to inches, so we know that has to be in the numerator. And we wouldn't write 2, we would say 1 inch over 2.54 centimeters, and cancel out those centimeters. And so now we would end up with 0.002 times 1 times 1, or we can just say 0.002 over 10 times 2.54. We have both of those numbers in the denominator. We just multiply those together. And so that would be 0.002 over 25.4. And so that's a really small number, 0.00079 inches. That is a really small diameter particle. But that's what clay is, and that forms sedimentary rocks sometimes. Now here's some big words here. After burial, sediment may undergo diagenesis. So not the erosion process that caused the sedimentary rock. That's what diagenesis is. There's other things that may happen, some different temperature and pressure combinations that affect it. And then it undergoes lithification. That diagenesis can result in lithification. So maybe the sediment is buried and then it gets soaked with some high silica-rich water. That causes the particles to cement together, and that's what lithification is, the forming of a rock. So sometimes it just stays as dirt and it gets blown around, or next time the rain creates some runoff, it just moves it around as sand and piles it up in one place, erodes it in another. And it never lithifies, it never forms a rock. That happens too. When it does form a rock, though, we have three different classifications. We have clastic sedimentary rocks. Those are composed of pre-existing rocks that are cemented together. Usually when we think of sedimentary rock, this is what we think of: a detrital rock like sandstone. And this sandstone here is from Antelope Canyon in Arizona, and you can tell it looks like at one point the sand was lying in this direction, and then maybe wind or water or both brought some more in and just cut that off, shaved that other part off, and formed this horizontal layer right there. And then there was some diagenesis that went on. Maybe some silica-rich water came through here and cemented things together and caused the lithification, turned that into solid rock. Now we have biological sedimentary rock that's formed from the accumulation of large numbers of dead organisms, mainly plants, cemented together. Coal is considered a biological sedimentary rock, and that's what this is in this image right here is coal. And then we have chemical sedimentary rocks, and those are formed from chemical precipitation. We've talked about that before. We're not talking about rainfall kind of precipitation here. This is when liquids come together or something happens in a liquid that a reaction takes place and solid falls out of that liquid. That's the precipitate that we're talking about. And when seawater evaporates, that's one way you can get a precipitate. And another way, a different way, is high pressures and high temperatures. We say HTHP for short there. That can happen in volcanic settings, and you get supercritical water, carbon dioxide and other fluids. And something interesting that happens there is that those can instantly precipitate many substances, including gypsum and halite. So let's say you had some salty water and that was flowing towards a source of magma, and water changes its properties as it gets warmer, and it can't dissolve as much halite or gypsum as its temperature increases, and so these fall out as solids. And you've seen this image over here before where all of this and hundreds of feet down is halite, and all of this and dozens, maybe hundreds of feet above that too is gypsum. That massive amount of halite and gypsum, one on top of the other, that probably formed by a high temperature, high pressure situation and not from just seawater evaporating at the surface. Sedimentary rocks are everywhere. They average over 1 mile thickness over the whole earth. If you could cover the earth with the amount of sedimentary rock that there is, just like make it into a smooth layer, like frosting over a cake, just over the entire earth's surface, it would average 1 mile deep, 5,280 feet deep. And so that makes me think that most sedimentary rocks formed during the Genesis flood or at creation. They formed during some high energy, highly erosive event that deposited lots of sediments, formed lots of sediments, but also some high temperature, high pressure reactions going on there that formed chemical precipitates as well in large basins that are all over the world. And this is something different about this earth science course that a lot of earth science courses probably don't talk about at all, is supercritical fluids, but I want to introduce those to you and just help you think about those a little bit more. And look at water here. We know that normal freezing point for water is 0 degrees Celsius at an atmospheric pressure of 1 atmosphere. That's normal atmospheric pressure. Water boils at 100 degrees Celsius or 212 Fahrenheit and a normal atmospheric pressure of 1 atm. Now, supercritical water, it acts different, and that's a high temperature. Look, 374 degrees Celsius, over 3 times higher than the normal boiling point for water. And look at the pressure, 218 times greater than normal atmospheric pressure. So these things happen under thousands of feet of rock or thousands of feet of water. And something to think about here, supercritical fluids, they require high temperature, high pressure conditions that might occur deep underground or deep underwater. And to the right is an image of a hydrothermal vent on the ocean floor, and you can see these solids coming out with some fluid along with them as well. But clearly something happened beneath the earth, probably close to a magma source. Water may have been flowing into that area and it couldn't hold all the chemicals in it anymore, and so those started to precipitate out. And then that liquid became less dense and it rose out these holes. So the study of supercritical fluids is helping scientists unlock many mysteries about the Earth. Well, let's look at metamorphic rocks now, the third main type of rock. And those are rocks that are formed by the alteration of existing rock by heat, pressure, and or chemically active fluids. And so we have some that are called foliated, others called non-foliated. Those are the two main groups of metamorphic rocks. Foliated, they have a layered appearance, like gneiss. And so you don't say that gneiss, it's like the word nice. And so we have an example over there to the right of an original rock, and all the sides look the same. They all have those rounded patterns in them. Now let's think about if that rock was flattened. These sides, they would look more linear, foliated, almost a layered appearance to them. And the U.S. Geological Survey illustrator here had a good sense of humor using the example of the rabbit and the flattened rabbit and then the stretched rabbit over here. This is another type of metamorphism where this side over here, it kind of looks the same as the original, but these sides look stretched out compared to the original rock. So those are two types of foliated appearances you might see in a metamorphic rock like gneiss. And then non-foliated, those really have no noticeable grain alignment. Like you can see it in this gneiss here. You can see these lines in that. It's pretty clear, that foliation. But here in this quartzite, there's no pattern there. So remember we said metamorphic rocks, those are formed from pre-existing rocks. Sometimes those are sedimentary rocks, sometimes those are igneous rocks, sometimes they're metamorphic rocks that they're altered again. And so we have limestone that can get turned into marble, sandstone into quartzite, and we just saw a picture of that. Shale gets turned into slate, bituminous coal into anthracite coal, gypsum into anhydrite. You'll be comparing some original and metamorphosed rocks in Lab Activity 1.5 as well. And so at the end of each of these Earth Science basic sections, I have a Why Study section. So now let's talk about why study rocks and minerals. Well, something to consider here is that all of us were created in God's image. That's what he says. He says he created us in his image, and says that in Genesis. And so that means that we're all designed to be creative too, because he's the ultimate, the most amazing creator, and he designed us like him. He made us in his image, so it makes sense that we're supposed to be creative too. And as Christians, something to consider as being good stewards and using the earth for serving others. A Christian is to take disorganized, messy things like rocks and minerals, turn them into beautiful, organized things that are useful to man and will help us properly manage his creation. That's something we'll be doing in Lab Activity 1.6, where you'll make a gold pan out of clay, and then Activity 1.7 you'll actually learn the gold panning process. And so in this example here, that's bauxite or aluminum ore on the left, and that's taken, turned into aluminum, which is worked and shaped to make an aluminum frame on a fighter jet like an F-16. So a disorganized thing over here on the left to an organized, very complex machine on the right, done by man. Man has taken this material from the earth and turned that into something useful. Now, something you may not have thought about is that everything you see around you that was made by man originally came from the earth. I mean, that's a self-evident truth, but it's just something maybe you haven't thought about much before. So think about this too. If you don't have a very good knowledge of rocks, minerals, other things that God made, that's going to limit your ability to be the creative person God designed you to be as well. And another good reason to study rocks and minerals is that every rock tells a story. That's like a fundamental statement in geology, in the field of geology. Every rock has a story. How did it get there? What's it made of? This is a fun and challenging thing to try and figure out. So rocks are more than boring clumps of nothing. They have a story and they have a use. And it's up to us to figure those things out. Okay, we'll go ahead and pause the lesson and work on your homework. So in your solutions, some that you had to think about a little more include problem 11, where the answer was pebbles and a 2-inch diameter sedimentary rock. You can convert that to millimeters because there's 2.54 centimeters in an inch, and maybe you realize that there's 25.4 millimeters in 1 inch. 2.54 centimeters, 25.4 millimeters is just times 10, and so that equals 50.8, and so that puts you in the range of pebbles. And then for boulders, well, a 12-inch is what you were given as the example, 12 inches, and again you can just say times 25.4, that equals about 305 millimeters, and so you can just look at that diagram and tell that's the category of boulders. And then problem 13, the maximum size of a sand grain. Well, we see its maximum size is 2 millimeters. And so we need to convert that to inches. And so we would say that 1 centimeter has 10 millimeters. And so our millimeters would cancel. And then we would say that 1 inch has 2.54 centimeters. And so we can make sure we have our unit multipliers the right way. That's a common problem on unit multipliers, is people will write them down flipped, inverted, the centimeters on the bottom, millimeters on top, when it's supposed to be the other way. And so we can always tell if we have them right if the numerator, millimeters, cancels the denominator. The numerator, centimeters, cancels the denominator. And so we have that set up right. And so we can see there we would just end up with 2 times 1 times 1, or 2 on top, over 10 times 2.54, or 25.4. And so that equals 0.079 inches. Okay, well that's all for lesson 1.3b.